Good morning, dear students. So, today's session we will focus on how to solve problems on performance testing of IC engines. So, first we will see some basic equations which are very useful for solving this problem, and then we will go for solving a problem based on performance testing of IC engines. So first, measurement of brake power. So we already know that brake power is the final power delivered by the engine, or it is the power that we are getting through the crankshaft of the engine. And the measurement of brake power, we require two things. One is the torque and another one is the angular speed. So the brake power will be T into omega, the rotational power or the mechanical power coming through the shaft of the engine. We can calculate by multiplying torque into angular speed, that is omega, and omega is 2 pi n by 60. So if you know the rotation per minute, capital N, which is measured by a tachometer, whether it is contact or non-contact, we will get N, capital N, the speed of the shaft, mostly in RPM. So we can use 2 pi n by 60. So omega is nothing but 2 pi n by 60, where n is the rotation per minute of the crankshaft. Now how to find the torque? For torque, we require a dynamometer. So a dynamometer is used for measuring of the torque. So the principle behind every dynamometer is that it will have a rotor attached to the shaft and a stator. So a stationary element is there as well as a rotating element. And some load must be applied to the rotating element. So whether through friction or through hydraulic energy, we have to apply the load on this dynamometer. And the dynamometer can be broadly classified into two categories. That is, first one is absorption dynamometer. So absorption dynamometer absorbs the power from the engine and it is dissipated as heat. So the friction, it will absorb this power and it will be dissipated as heat. So most of the dynamometers are absorption type dynamometer. So rope brake dynamometer, Prony brake dynamometer, hydraulic dynamometer, eddy current dynamometer, all these are absorption type dynamometer, because all these will absorb the power from the engine and dissipate it as heat. Mostly we will be using rope brake dynamometer. In the problems, mostly we can see the dynamometer will be a rope brake dynamometer. You might have already used in your thermal engineering lab. And all these things worked on the same principle, applying load to a rotor and through a stator. But how the load is applied is different. For example, in rope brake dynamometer, we will be applying weight, and that weight will act as a load. But in hydraulic dynamometer, we are using hydraulic energy of fluid, mostly water. So it differs. Then transmission dynamometer, the power of the engine is transmitted to the load. So they are not absorbed. The load power is transmitted to the load after it is measured. They are also known as the torque meter. So we will be mostly using this rope brake dynamometer in the problem. So how to find brake power using a rope brake dynamometer? So this is a rope brake dynamometer. You can see this is the brake drum attached to the engine shaft. A rope is surrounded at this like this, and we have the freedom to hang the weight. So we can add weights from 0 to some maximum weight we can add, and the spring balance is provided for balancing this weight. So a spring balance reading will be here. So weight we can measure, and the diameter of this drum and the thickness of rope etc. will be known quantities. And another thing is we have to supply the cooling water because the power is dissipated as heat after the load is supplied. So we have to continuously supply a cooling water to this brake drum. Now how to find the brake power in this setup? So we have to use the basic equation, that is brake power is 2 pi nt by 60. Now you know n by the tachometer, we know the RPM value. So how to find torque? Torque is force into distance. So force is the net force or net load is W minus S, the weight. So what is W? W, N is the speed of the engine in RPM. T is the torque acting in the dynamometer in Newton meter. So W is the weight at the end of the rope. So this weight. An important thing is it should be in Newton. So the SI unit of weight is Newton. Similarly, S is the spring balance reading. So these two readings must be in Newton. If in some problem this W is in kilogram or this S is in kilogram, we have to multiply by acceleration due to gravity G. So you have to multiply by 9.81 if this W and S are given in kilogram. But if it is in Newton, we can directly use this relation. Torque is equal to W minus S into dB plus. So this is the effective diameter of the brake drum. So what is the effective diameter? Effective diameter is dB plus D. dB is diameter of the brake wheel in meter and small d is diameter of the rope. So if the rope diameter is given and if the brake wheel diameter is given, we have to add this and divide by 2 because the force will be acting through the radial distance from the center. So this is the equation used for finding out torque. T is equal to W minus S into dB plus D by 2. So this is the effective diameter of the brake drum and W and S should be in Newton. Now how to find indicate power. Indicate power is the power developed inside the cylinder. So for measuring indicate power, the indicator diagram should be there. The pressure volume or pressure crank angle diagram is known as the indicator diagram. So from that we can find the mean effective pressure, the average pressure acting on the piston. In one cycle we know that mean effective pressure, which is already you have studied that. So indicate power we can find out by an indicator diagram, and for indicator diagram we want an indicator device. So in the lab etc. you might not have done this indicator power measurement because it is a costly equipment. The indicator device requires 3 elements. First is a pressure sensor. Pressure sensor is required for sensing the pressure at one cycle. Then a displacement sensor, the piston displacement sensor, and a display unit. So 3 units are required: pressure sensing device, a display sensor and a displacement sensor and a display device. So using this only we can draw a indicator diagram. So how to calculate indicator power? For 4-stroke engine we can use this equation. Indicator power is equal to mean effective pressure PM, that is obtained from an indicator diagram, into this represents septic volume, area into stroke length AL, and N by 2. What is N? So N is the RPM, and why we are dividing 2 in 4-stroke, but in the 2-stroke engine you can see the only difference is we are not dividing N by 2. We are using N as such, but here we are dividing N by 2. This is because that in 4-stroke engine 1 power stroke will be generated in 4 strokes of the engine, or in other words, in a 4-stroke engine the 2 revolution of crankshaft, so 2 strokes are equal to 1 revolution of crankshaft, because 1 stroke is equivalent to 180 degree of crankshaft. You might have already know that 1 revolution of a crankshaft means it is 2 strokes. So 4-stroke engine, to complete the 1 working cycle, that is to complete one suction, compression, power and exhaust, we require 2 revolution of the crankshaft. So that means the working cycles in n revolution will be only n by 2. So if you have 300 rotations, the working cycle will be only 150. So that is why we have to divide n by 2 in 4-stroke engine. But in 2-stroke engine we have only 2 strokes. One power stroke is there in this. So it is power stroke is produced in 1 revolution of the crankshaft. So we can take n as such, because 300 rpm means we have 300 cycles. So that is why we are not dividing n by 2 here. So that is, we have to note down, if the 4-stroke engine we are using this equation, 2-stroke engine instead of n by 2 we can take n itself. So PM is the indicated mean effective pressure, and its SI unit is Newton per meter square. So if it is in bar, you have to multiply by 10 raised to 5. Area A is the area of piston, L is the stroke length. So A into L will be the swept volume. N is the speed of the engine, and small n is the number of cylinders. So if the number of cylinders, multi-cylinder engine, the number of cylinders 2, 3, etc., you have to substitute n as 1, 2, 3, etc. So using this equation we can find the mean effective pressure. But how to find the, indicated power. So how to find this mean effective pressure? If you have the indicated diagram, this area and length we can calculate. So mean effective pressure is nothing but small a by small l into K. What is small a? Small a is the area of indicated diagram. Small l is length of the indicated diagram, because it is the average height of that diagram. That is why we are taking area of indicated diagram to length of indicated diagram. And K is the spring constant, because the unit, if the area unit is meter square, length will be meter. So by A by L you will get meter. But pressure unit is different, so you have to multiply by the spring constant of that indicated device K, and that will be mostly in bar per centimeter or bar per meter, etc. So we can find the mean effective pressure using this equation. And how to find equations for efficiency? We have different efficiency in an IC engine, not like mean of mechanical efficiency, brake thermal efficiency, indicator thermal efficiency. So we have to know the different ratios. So finding out this efficiency, we require heat input. So how to find the heat input to the engine? Q1. Q1 is also known as fuel power. So that is, we can find out by multiplying mass flow rate of fuel into calorific value. So that means heat input to the engine is, or fuel power is equal to mass flow rate. So this can be obtained from fuel consumption. So fuel consumption we can measure using a burette or some other device. So that will be in volume per second. So you have to convert that into mass flow rate and multiply by the calorific value, because each fuel we have a calorific value. Calorific value is defined as heat liberated by burning 1 kilogram of a particular fuel. So for example, for petrol it is 42.5 kilojoule per kilogram. That means if you burn 1 kilogram of petrol, it can produce 42.5 kilojoule energy. So that is the meaning of calorific value. So it will be a standard value and given for different fuels. So mass flow rate, MF is a mass flow rate in kilogram per second. Calorific value, the SI unit is joule per kilogram, but mostly we will be expressing in kilojoule per kilogram or megajoule per kilogram. So you must be careful with the unit. If the calorific value is kilojoule per kilogram, you will get Q in kilowatt, and if it is joule per kilogram, you will get Q in watt. So like that we have to take. Now break thermal efficiency. What is break thermal efficiency? Eta BTH. It is the ratio of break power to heat input. So BP by Q in or Q1, and expressed as percentage into 100. Similarly, indicated thermal efficiency is indicate power by heat input into 100%. And finally, we have mechanical efficiency, which is break power by indicate power. The ratio of break power to indicate power is known as the mechanical efficiency. So these three efficiencies are very, very important. Then we have specific fuel consumption, SFC. What is SFC? So it is defined as the fuel consumption rate required for producing 1 kilowatt break power. Normally break power we take it as kilowatt. So it is the fuel consumption rate required for producing 1 kilowatt break power. So how to calculate that? Simply we can get SFC by this fuel consumption or mass flow rate divided by break power, and it is expressed in kilogram per kilowatt hour. So normally SFC, this fuel consumption will be taken in kilogram per hour. So that is why we are getting SFC as kilogram per kilowatt hour. So what is the meaning of this? Suppose you are using an engine and its SFC is 0.5 kilogram per kilowatt hour. What the meaning is that engine can produce 1 kilowatt brake power using 0.5 kilogram per hour of that fuel. So that means the FFC is less, that much better the engine will be. So if the FFC, we have to reduce the SFC value for getting good performance. And finally we have volumetric efficiency, another efficiency defined as the ratio of actual volume of charge. That is mean by charge means the air fuel mixture or the air only. In diesel engine it is the air only, in petrol engine it is the air fuel mixture. So actual volume of charge inhaled during suction stroke, measured at intake conditions or normal temperature and pressure, to sept volume. So it is the ratio of how much volume of air or charge is coming during suction stroke to the sept volume. Now we for solving one problem. This is the problem. Let's solve this. The following observations were recorded during the trial of a 4-stroke single-cylinder diesel engine for a duration of 30 minutes. Fuel consumption is 4 liters. Calorific value of fuel is 43 megajoule per kilogram. Specific gravity of the fuel is 0.8. The average area of indicator diagram 8.5 centimeter square. Length of indicator diagram 8.5 centimeter. Spring constant 5.5 bar per centimeter. Brake load is 150 kilogram. Spring balance reading 20 kilogram. Effective brake wheel diameter 1.5 meter. Speed is 200 rpm. Cylinder diameter 30 centimeter. Stroke 45 centimeter. Calculate indicate power, brake power, mechanical efficiency, specific fuel consumption in kilogram per kilowatt hour, and indicated thermal efficiency. So this problem we have to solve. How to solve this? Let's see. So first we have to write the given quantities. So small a is given, area of indicator diagram 8.5 centimeter square. Length small l is, so we are using the small l because we are using capital L for stroke length and capital A for the cylinder diameter area. Now small l is 8.5 centimeter. Now spring constant of indicator device 5.5 bar per centimeter. W is 150. The dynamometer weight added is 150 kilogram. So it is only in kilogram, not in Newton. Spring balance is 20 kilogram. the mean diameter or the effective diameter is given. So no need to take the rope diameter etc. because the effective diameter is directly given 1.5 meter. Speed is 200 rpm. Specific gravity 0.8. Now another thing given is number of cylinders only 1. Calorific value is given 43 megajoule per kilogram. This is the fuel consumption 4 liters per second. And this is the diameter of cylinder or and the stroke length. Now we have first step is find out the mean effective pressure PM. So PM is find out by area divided by length, area of indicator diagram divided by length into spring constant. So all these are given and its unit is 8.5. So centimeter into spring constant is bar per centimeter. So centimeter will cancel and we are getting mean effective pressure as 5.5 bar. So its SI unit is Newton per meter square. So it will be 5.5 into 10 raised to 5 Newton per meter square. Now once the mean effective pressure is calculated, we can find the indicate power. So indicate power is, this is a 4-stroke engine, so we have to use N by 2. So main effective pressure into area length into N by 2 into N by 60. So 5.5 into 10 raised to 5 is the mean effective pressure. Area is pi by 4 d square. So here we have to convert that into SI unit. 30 centimeter is the diameter. So 0.3 meter we have to take. Pi by 4 into 0.3 square. Length is 0.45 meter. Speed is 200 divided by 2 because it is a 4-stroke engine. Small n is 1. So we are getting all of these must be in SI units. Then we will get in watt. 29,160 watt. That means 29.16 kilowatt. So that is the indicated power. Now how to find brake power? So for that we have to use brake power is 2 pi nt by 60 and torque is W minus S into dm by 2. dm is the effective diameter or mean effective diameter of the brake drum. So that is also given. But here W and S are given in kilogram only, but it should be Newton. So we have to multiply this by 9.81. So that means brake power is 2 pi into N is 200. Torque is this 150 minus 20 into 9.81 into dm by 2, 1.5 by 2 divided by 60. So by solving this, we will get 20,030 watt. So that means this 20.03 kilowatt. So the unit you should be very careful. Once the unit is wrong, you might have end up in wrong values. So that is why we are doing all this in SI units. Then we will get watt and we can divide by 1000 to converting to kilowatt. So 20.03 kilowatt. Now mechanical efficiency we can directly calculate because it is the ratio of brake power to indicate power. So mechanical efficiency is BP by IP into 100%. So we are getting 68.7%. Now at indicated thermal efficiency we require heat input. So how to find heat input? For that we require the fuel consumption or mass flow rate of fuel. So for finding the mass flow rate of fuel, volume is given. Only here it is given 4 liters is consumed in a duration of 30 minutes. So that means volume flow rate will be 4 liters. We have to convert into meter cube. So 4 into 10 raised to minus 3, that much meter cube divided by 30 minute it is taken. And we are expressing it in hour. So again we have to multiply by 60. This is because fuel consumption is normally expressed in kilogram per hour. So into 60. Now this is volume flow rate. To convert that into mass flow rate, we have to multiply by density. So what is the density of this fuel? We get specific gravity is given 0.8. Specific gravity is the ratio of density of that liquid to density of water. So that means density of this fuel is 0.8 into 1000. 1000 is the density of water. So we are getting fuel consumption as 6.4 kilogram per hour. So using like this we can find the fuel consumption. Mostly volume flow rate is given. So convert that into meter cube per hour and multiply by density. Now specific fuel consumption is ratio of this fuel consumption in kilogram per hour to brake power. So directly we can get specific fuel consumption 6.4 divided by 20.03. So 0.3195 kilogram per kilowatt hour. Now heat input or fuel power you have to find out. For finding this indicator thermal efficiency you require heat input. So heat input is mass flow rate into calorific value. But again in the unit you have to be careful, because now the mass flow rate is in kilogram per hour, but here we want kilogram per second. So divide this by 3600. So mass flow rate is 6.4 divided by 3600. Now it is in kilogram per second. And multiply by calorific value. Calorific value 43 megajoule. 43 megajoule per kilogram. That means 43 into 10 raised to 3 kilojoule per kilogram. So now the obtained value will be in kilowatt. So this unit be very careful. For heat input we have to use mass flow rate in only kilogram per second. But mostly we will be getting mass flow rate in kilogram per hour. So you have to divide that by 3600. Similarly calorific value, if it is in kilojoule we will get directly kilowatt. So now that is why we are multiplying to 10 raised to 3. So now we have obtained heat input 76.44 kilowatt. Now what is the indicated thermal efficiency? Indicated power by heat input. So that means indicated power already we have obtained 29.16. So indicated thermal efficiency will be 29.16 divided by this 76.44 into 100. So finally we are getting indicated thermal efficiency as 38%. So you have to solve this problem using different textbooks. Numerous problems in these reference books. So you have to solve by yourself. Thank you.